In this lesson, we will learn about the concept of asymptotic notations as a way to classify the running time of algorithms into some generic and broad classes or sets. In the previous lesson, we had seen how to calculate the running time expression for algorithms using the concept of a hypothetical model machine. So why do we really want to classify the running time of algorithms into these broad classes? Let's say we have two algorithms. Algorithm 1 has the running time defined by this particular function Tn is equal to 5n square plus 7, where n is the input size, and algorithm 2 has the running time defined by 17n square plus 6n plus 8. And let's say we have reduced these expressions on a model machine. We had defined the concept of a model machine in the previous lesson. A model machine has some basic operations, and each basic operation, like arithmetical, logical, or assignment operation, costs us 1 unit of time. Now these functions are corresponding to the model machines, but we want some functions or some representation which is true irrespective of the machine and still gives us the idea about the rate of growth of time. Now, a couple of things about time complexity analysis. When we analyze time complexity, we analyze it for really large input sizes. So we want to analyze the time taken when n tends to infinity. In this case, if n tends to infinity, this plus 7 in the first function and this plus 6n plus 8 in the second function will become insignificant, corresponding to the n squared term. And if n tends to infinity, this constant multiplier 5 and 17 also become insignificant. And these two functions will pretty much have the similar rate of growth for very high values of n. So irrespective of the machine used, we can say that these two algorithms have something like a quadratic rate of growth, a rate of growth which is defined by a quadratic function, which kind of brings these two functions in the same class. But we have a very formal way of classifying functions into classes in the form of asymptotic notations, where we do not have all these constants in the expressions and we only have the variable term. And let us now define these asymptotic notations, and the first asymptotic notation that we want to define is the big O notation. If we have a non-negative function gn that takes a non-negative argument n, then big O of gn is defined as the set of all the functions fn for which there exist constants, some constants c and n naught, such that fn is less than or equal to c times gn for all n greater than or equal to n naught. And it's easier to understand this using some example. Let's say we have a function fn equal to 5n square plus 2n plus 1, and we have gn equal n square. Now let's see, this 2n can never be greater than 2n square, and this 1 can never be greater than n square. So if we use c equal 5 plus 2 plus 1, which is 8, then fn is always less than or equal to 8n square for all n greater than or equal to 1. So for c is equal to 8 and n naught is equal to 1, we can say that fn is an element of the set big O of n square. And we often also say this as fn is equal to big O of n square. And let us now plot these two functions on a graph. So we have plotted the graph here, and you can see that after n is equal to 1, that is our n naught, c of gn is always greater than fn. So this assures that fn never grows at a rate faster than c of gn after n naught. So in this way, big O notation kind of gives us an upper bound of the rate of growth of a function. And in time complexity analysis, this is very useful because we can say that, hey, this is the upper bound of the rate of growth of time, and the time cannot grow faster than this. Now, one more important thing here is that this c and n naught can be chosen differently. So for the same function fn and gn, we can choose different c and n naught, and still our conditions may be valid. So let us now define another asymptotic notation, and this notation is called omega notation. And the definition for this notation is that if we have a positive function gn that takes positive argument n, then omega of gn is defined as the set of all the functions fn such that there exist constant c and n naught for fn, so that c of gn is less than or equal to fn for all n greater than or equal to n naught. Let's pick up an example again, and let's pick up the same example that we had picked up the last time. Let's say our function fn is 5n square plus 2n plus 1, and our function gn is n square. Now for all n greater than or equal to 0, this 2n plus 1 will be greater than or equal to 1. So if we have c is equal to 5 and n naught is equal to 0, then clearly 5n square is less than or equal to fn for all n greater than or equal to 0. So we can say that fn is omega of n square. And let us now plot this on a graph. What this graph tells us is that c of gn will never exceed fn for all n greater than or equal to n naught. So omega notation gives us the lower bound of the rate of growth of a function. And in the context of time complexity analysis, this may be important in the sense that we may say that hey, the time taken grows at least by the rate of growth of this particular function, gn. And let us now see the third asymptotic notation, which is called theta notation. And the definition for this function is that if we have a function, a positive function gn that takes positive argument n, then theta of gn is defined as the set of all the functions fn such that there exist constants c1, c2 and n naught for fn such that c1 times gn is less than or equal to fn, which is less than or equal to c2 times gn for all n greater than or equal to n naught. And let us pick up an example again. And if we pick up the same example that we had picked up earlier for big O and omega notation, fn is equal to 5n square plus 2n plus 1 and gn is equal to n square, then we can choose c1 equal 5, c2 equal 8 and n naught equal to 1, and our inequality will hold, and we can say that fn is actually theta of n square. Now of all the three asymptotic notations, big O, omega and theta, that we have defined, theta notation best describes or gives the best idea about the rate of growth of the function, because it gives us a tight bound, unlike big O and omega, which give us upper bound and lower bound. So theta notation kind of tells us that gn is as close to fn, the rate of growth of gn is as close to the rate of growth of fn as possible. And let's now plot this on a graph. So we can see in the graph that fn is bound by these two functions c1 gn and c2 gn after n is equal to n naught. So this fn always lies between these two functions. In time complexity analysis, we should always try to find the tight bound expression or the theta notation of the time taken, because that gives us the best idea about the time taken. But we also in a lot of cases use the big O notation, which gives us an idea about the runtime of the algorithm in the worst case. So these were the three asymptotic notations that we use for time complexity analysis. In coming lessons we will pick up different kind of algorithms, different kind of complex algorithms as well, like recursion, and see how to analyze and deduce these asymptotic notation expressions for them. So thanks for watching.